Complex numbers. I want to give you just a little bit of history on complex numbers. The person that first discovered it was Heron, and he's of Alexander. He is a Greek mathematician. It was first written by, and I'm not going to say this name correctly, so I'm just going to spell it out here for you, in 1572. So let's talk about imaginary parts. Whenever we go solve a problem and we put it on a graph, sometimes we come up with a part that's not real. It's there, but it's not real. So they come up with a name for it and called it the imaginary part, because we couldn't discard it because something is there, just it wasn't real. And I know that sounds crazy. So imaginary numbers are said to be first discovered by Heron, the Greek mathematician. So I thought that was pretty interesting. It was dated back to 1572. Well, let's just talk about it. The imaginary number is represented by the little lowercase I. And how do I know that I have imaginary part? Well, if we take an even root of a negative number, just an even root, well, this even root tells me that we're going to multiply this negative an even amount of times and still come out with a negative, which is not true. So this is where I'm talking about that there's something there. It's just not real. This is not a real number because it's not a true statement. So therefore, it is said that I is equal to the square root of that -1. Well, if I was to say, okay, I need to solve for that what's inside that root, that means I got to undo the root. And since it's a square root, I'm going to raise it to the power of 2. So now I get I squared, which is equal to -1. And that's where we know this statement is true. Okay. So whenever I talk about roots, let's just for a moment talk about what we know about roots. All right. So whenever I have a root, this number here is called our index. It's also can be called the root. If there's no number there, then we know it's a square root because the square root is the smallest root there is. But if it's a cube root, a fourth root, and so on, you'll see the number there. Whatever is inside here is called the radicand. And whatever power it's raised to is power. It's called power. We can also write it like this, raised to the power as well. So these two statements here is showing you two different ways to write it. So let's move on. Now let's talk about our notation here. I to the first, well, we know that's I squared. We've already figured that out. It's -1. I cubed is -I. I to the fourth is 1. And anything after that repeats. So how do I know? It repeats. So I to the fifth is I to the sixth is -1. I to the seventh is I to the eighth is 1. Repeats again. So this is telling me every fourth one, we're going to come out with the number 1. The definition of the set of complex numbers is the set of the real part, which we're going to call A, plus or minus the imaginary part, which is BI. A and B are considered as constants, and the I with the B is letting us know that that's the imaginary part. Here are some formula, or it's not formulas, it's just letting you know that like when we add a binomial of a real part plus an imaginary part, whenever we add or subtract, we can't put unlike terms together, right? So we only can put like terms together. So we got addition of this real part plus this imaginary part, this real part plus imaginary part. What we're going to do is pull the two reals out and add them together, pull the two imaginaries out and add them together. We're going to do the same thing on subtraction, except for we're going to distribute that negative sign. Whenever we take the product, we're going to distribute or use the full method. So the real can be multiplied to the imaginary part and so on. So we're going to do that. And this is just letting you know This is helpful information to help you solve if you're given an adding or subtraction or multiplication of a complex number. This one here is telling me, okay, if I have a binomial of a complex number, I have the real part at the beginning of both parentheses that are identical, and imaginary part in the both parentheses that are identical, but the signs are different. I got a plus and a negative. Then I know that we're just going to square the first and square the second, and the middle goes away. And we're going to solve some, and I'll show you what I mean by that. So this is just a theorem, and it's a shorthand notation. I'm not saying you have to do it this way, but sometimes it's helpful. Division of complex numbers. We cannot have an imaginary number in the denominator. In the denominator, you can't have an imaginary, you can't have a root, whatever that root is, it doesn't matter. You can't have a fraction, a decimal. Let's see what else. And there's something else. And you can't have a zero. But these here we can work with. There's a rule we can follow to undo this, and that is taking the conjugate of these two. We can take the conjugates and undo these. These here will apply the basic math rule. But if we have zero in the denominator, then it's just undefined. There's nothing we can do about it. And I'll add to this list if I come up with another one here. So we're going to take the conjugate. So how do I know what the conjugate is? Well, that goes back to here. So the conjugate is, I see that that's C plus the DI, then that means I would just multiply it by C minus DI, where the signs are different, right? The signs are different, but the first in the parentheses and the last in the parentheses are identical. So that just leaves me with the first squared and the last squared, and it throws away the middle, and the imaginaries go away. All right, the roots of a negative number. It says that positive real B, number B, says that if I have the square root of negative B, because square root says whatever we multiply is going to be an even amount of times, then that means the negative will go away. And in this case, it doesn't. So therefore, we need to represent what is that negative. We're going to pull the negative one out. Negative square root of negative one is I, so it leaves me with square root of B. So let's solve. Let's get started here. So we're going to perform the indicated operation. This says we're going to subtract. So that means we cannot put the real parts and the imaginary parts together. So what I'm going to do is I'm going to pull the real parts out, but make sure and distribute the negative sign. So I got 10 minus that 7, because 7 is positive times that negative. And then I'm going to take this negative I and pull out that imaginary part. Well, I distribute that negative sign to the 3. Now I can put my like terms together. 10 minus 7, negative I minus 3. That's the same as saying I'm in the whole $1 and I spend 3 more. So now I'm in the whole $4. And that is my answer. Okay, our next one says we're going to multiply. So if you notice, the first terms are identical, the last terms are identical, but the signs are different. So this is where we can follow that rule, where we can square the first, right? And we're going to say minus the last squared. Oops. Let me put that 2 on the outside of that parenthesis. All right, so now I got 2 squared, which is 4, minus 5 squared is 25. I got I squared. I'm doing extra stuff here. Well, I squared is -1, negative times negative. So 4 plus 25 is 29. So that would be my answer. Now let's just double check, okay? Why you in the distributive property. So if I was to take this here, or use the full method. Let's use the full, because they're binomials times binomials. So we got our first times our first. So 2 times 2 plus outers, 2 times that 5i plus 2 times that negative 5i plus a negative 5i times 5i. All right, so 2 times 2 is 4. 2 times 5 I is positive 10i. And 2 times a negative 5i is negative 10i. Negative times positive, so 5 times 5 is 25, I squared. Now I got 4. What happens? The middle goes away. 10 minus 10, right? That goes away. Now I got 25 times negative 1, which is 4 plus 25, which is 29. So if you need to use this long method, go for it, okay? If this makes sense, then use the shortcut. However, if you look at example 3 here, the first terms are not the same and the last are not the same, so this rule is not going to work. So we're going to have to use the full method or distributed method here. I'm going to use the full again because it's binomial times binomial. So I got my first times my first, plus my outers times my outers, plus my inners, which is times the inner, and then my last. All right. So now I got 3 times 2 is 6. 3 times 9i is 27i. Negative 7i times 2 is negative 14i. Negative times positive is negative. 7 times 9 is 63. And I times I is I squared. So now I got 6 plus, because $27, if you have $27 and you spent 14, we have 13i. And then I got this negative 63, but I squared is negative 1. So now I got 6 plus 13i plus 63. And we're going to put the 6 and the 63 together because they're like terms. And we're going to write it as the real plus or minus the imaginary. Now let's solve example 4. Example 4 says I have I to the 95th. Okay, so at the beginning I talked about if we have I to the first, we get I, and it goes down to I to the fourth, excuse me, 1, and it repeats. This was very important because if I can write this as a power of I to the fourth, I know whatever is inside here will be 1, right? Because I to the fourth is 1. So what I need to do is take that 95 and divide it by 4 and figure out how many times 4 are going to 95. So I get 4 times 2 is 8, subtract 9 minus 8 is 1, bring down the 5, 4 times 3 is 12, with the remainder of 3. So what I need to do is say that 4 times 23, because if you raise it to a power and raise it to another power, then we multiply the powers. So 4 times 23 will give me 92, okay? It leaves me with a remainder of 3, so I need to raise the I to a 3, because now if I add the powers, right? Whenever you multiply like bases, you add the powers. That's 1 plus 1, right? But if you raise it to a power, you multiply the powers, all right? So knowing this, now I got it written in the format of this is still equal to I to the 95th power, but it's workable now. I know I to the fourth is 1 times I to the cube, which is what, negative I. Now 1 to the 23rd power is just 1 times that negative I, and my answer is negative I. All right, example 5 says we have an I, an imaginary part in the denominator. So I'm going to multiply by I because we need to multiply by its conjugate, whatever it's going to take to undo it and get I out of the denominator. I know if I multiply the denominator by I, then I'm going to get I squared. And we know what I squared is. It's going to be negative 1. Okay. Now I'm going to say I times 2 is 2I plus 7I times I is 7I squared. So now I got 2I plus 7 times negative 1. And now let's just rewrite it, 2I minus 7 over negative 1. Now, what I'm going to do is take this negative sign and bring it to the top and distribute it. So I got negative 2I, and then that negative times that negative gives me a positive. However, we need to write it in the standard form of real and plus or minus imaginary. So I'm going to say 7 minus the 2I. And that is my answer there. Okay. Let's go to the next one. The next one has 5 plus I in the denominator instead of the just I. So let's multiply it by its conjugate. And remember, we want the first and the last to be identical, but we want the signs to be different. And since this is a plus, I'm going to put a negative. And what we do to the bottom, we have to do to the top. All right, so now what we're going to do is, if you want to use the shortcut, you know the first squared minus the second squared. You can do that. If you want to distribute to the full, then do that, whichever works best for you. On the top part, however, the first and last are not identical, and the signs are different, but the first and the last are not identical. So we're going to do the full method, 4 times 5 plus 4 times that negative I plus 3I times 5 plus 3I times that negative I. All right, so now let's clean up. I got 4 times 5. I got positive 4 times negative I. I got positive 3I times 5. And then I got a 3I times a negative 3, or excuse me, a negative I, all over 5 squared minus I squared is negative 1. All right, let's clean up some more. I got 20. These two here we're going to put together. So I have $15. I spent 4. Now I have 11. This I squared becomes -1. I'm doing an extra step. Some of you will not need this many steps. So negative times negative is positive. All right. So now I got 20 plus 11i. That negative times negative becomes a positive. 25 plus 21, or excuse me, 25 plus 1 is 26. And now I'm going to put these two together, and I got 23 plus 11i over 26. However, we're going to write it as real versus imaginary. So I have 23, 26 plus 11, 26. Now, this I either goes out to the side or you can put it in the numerator, but do not let it go in the denominator, okay? Let's erase this. And this is our answer. Okay. Our last one here. It says we have a binomial plus a binomial. So that means we can only, since we're adding, we can only put the identical to, or not, like terms together. We can only put like terms together, okay? So in this case, the real goes together. So I got 6 plus 4. And then the imaginary parts go together. 5i minus 4i. And then clean it up. 6 plus 4 is 10. 5i minus 4. So we have $5, you spent 4. So we have I. And that is our answer.